So we will continue our discussion on I/O and storage systems. So keep in mind we have had 2 lectures on file systems already. We talked about the file system interface, all the system calls in the first lecture, and then we talked about file organization. We looked at linked list organization on this contiguous allocation. We talked about notion of multi-level index structures and inodes and whatnot. Okay, those were the 2 classes, and today we are going to talk a little bit in more detail about the disk itself. Okay, how does it actually service I/O requests that are coming to it from the OS? Okay, and then I'll also talk a little bit about other storage devices. Solid state disks, tape drives, and RAID storage, just to give you a sense of how other storage systems interact with the OS. Okay? And then next time we are going to talk about I/O systems, okay, more generally I/O devices. So until now, all of this discussion has been focused on a single I/O device, namely the disk, okay, the most important one probably, other than the screen. Okay, so this is a recap of what I showed you last time. This time I did bring a CD just to show you. This is basically the platter that is inside a disk, very similar to CD or DVD RAM drive. Typical disks have a stack of these, okay, platters, so each of them is a surface on which data is recorded. So you will see that the data is recorded in concentric tracks. Okay, the disk spins, and there's a disk head that moves back and forth. So that's your disk head. If it's positioned there, then it can read whatever is right underneath it. Okay? And as it's spinning, you can basically read the entire track. If you want to read another track, you have to move the disk head back and forth and position it on the right track. Okay? The overhead to move the disk head to the right track from wherever it is called the seek time or the seek latency. Okay? The time it takes for the right sector, once you're positioned on the right track, the latency it takes for the right sector to spin under the disk head is referred to as the rotational latency. Okay? So if the disk head, if the sector has just spun by, you have to wait for an entire rotation before it will spin by again. So the rotational latency can be as much as an entire rotation of your disk, and on an average it's half the total rotational time. And the transfer time is the time to actually transfer data, read or write bits from sector. Okay, so typically disk I/O time is the sum of the seek time, the rotational delay, and the transfer. And that is, and as I mentioned, these 2 quantities are effectively wasted time from a disk perspective. The reason disk I/Os are slow is because these overheads are significant. They can be in the order of milliseconds or tens of milliseconds. For every I/O request, you have to wait 20 milliseconds even before the disk can do anything. That's a significant overhead. This is why disk I/O is slow. And so we are going to look at, in today's class, techniques to optimize the seek and rotational latency from the disk's perspective. Last time we looked at techniques to optimize it from the file system perspective by placing data close to one another or coming up with index structure that allow you to do efficient random access. Okay. Somewhat old table, but nevertheless representative, so I think in order to change it. Okay, so typical disks here, SATA disks, SCSI disks, you must have heard of this term, SAS disks, and so on. Okay, so this is about 5 years old now. I haven't changed it, but it's represented. So you'll see the characteristics of a typical disk. Okay, so number of platters per disk, that's 16 and 8. That basically means there are either 16 or 8 of these packed into a 2 inch thickness. Okay, so there's quite a bit of data being stored on each, and then there are 16 ones. Okay, number of tracks per surface, that's the number of concentric circles on which you can record, on the order of thousands. Okay, 6 to 16 thousands, and now as disk capacity has increased, that number keeps going up. Okay, so you need a fairly fine disk head if you are to actually write 16,000 tracks of data on this. Okay, so keep that in mind. Sectors per track varies. Bytes per sector typically is a few hundred, 512, 732. Some of them might have 10245, but mostly 512 is a good number. RPM has been increasing. Okay, that's a 7,000, 7,200 RPM. This is a 15,000 RPM. That basically says how quickly is this platter spinning. Okay, So the faster it spins, the faster you can actually read data or write data, and lower the rotational latency. Now clearly that number can't keep going up, because as you need faster and faster more motors to spin this thing. Okay, and that means it will consume more energy. The disk will heat up more because the motor that's spinning is very good. Okay. Average seek time 4 milliseconds, that's basically what I was saying. Average rotational latency all in the same order. Okay, rotational latency is completely governed by the rate at which this platter is spinning. Okay, this is effectively half the time for half a rotation. Okay, so you will see that this is roughly twice of the rotational latency and half. Okay, a few milliseconds. Okay, and that's the transfer rate. That's governed by the interface, whether it's SCSI or SATA or whatever interface you have. Okay, the disks also have buffers on them, so they can actually buffer data internally before transferring data out on the order of few milligrams. Okay. Just to give you a feel for what kinds of characteristics we are looking at. Any questions on any of this? Observations, yes.
Is the average seek time affected by the number of tracks per surface?
Is the average seek time affected by the number of tracks? Well, it depends on the speed at which the disk head can move. It depends on whether it's a 3.5 or a 2.5 inch. If it's a 2.5 inches, this is a smaller platter. Okay, so you have to only move approximately an inch. Here you probably have to move 2 inch. Okay, so the speed at which you can move, the size of the platter, these are the things that actually govern the seek time. Of course, if there is more tracks, okay, that doesn't make the head slower, but you need the head to be more precise. So what happens is, typically if you look at the way disk head, if you want to move from the inner track to an outer track, the disk head will start moving, it will accelerate, and it will coast along, and then when it approaches the disk head, it will start decelerating, just as you would drive a car, right? So you speed up, you go to steady speed, and you stop. The same kind of stuff happens. And if this surface area keeps shrinking, there's not enough time to coast. You'll accelerate, you'll get there, and you start decelerating. So that all of those govern how much time it takes you to seek those parameters. Okay, if you don't decelerate in time, you'll overshoot. And then typically you don't want to do that. Yes.
So the disk spins at 1700 RPMs for the full length. It doesn't actually slow down when you do it.
The disk is continuously spinning in most systems. So the only reason it will not spin is if you have OS level power management, which says there is no I/O whatsoever. Then the OS will actually send a command to the disk and spin down. Because I mean, you're just wasting energy by keeping the disk spinning.
I was actually thinking of like laptop sensors that if you move it a certain way, they will stop the
so that's the other thing. I was going to say the only other reason for the disk to spin is most of these disks have a motion sensor. If you actually see sudden motion, they will stop the disk. The reason is if you have 16 of those platters, okay, they're tightly packed, and if you actually go and bump your laptop on a table, this thing is going to move. Okay, it's not going to be steady. And if it moves and the disk head actually goes and touches the surface, it can potentially damage the surface. Okay, so if it actually, so you have a sudden motion sensor, so if you actually, it feels like the machine is moving because you dropped it or something happened, it will sort of call for an emergency stop, so this thing will stop spinning to prevent accidental damage. Okay. But that is rare. The more common case is power management, where there's no I/O, the disk will spin down.
So it will also like retract the head from...
Yes, you will retract the head and stop it, because the head is, when it's parked, it is more steady. If it's just hanging there, it will go and potentially hit something. Okay. But typical case is if you have no power management, it will keep spinning. In most servers, it keeps spinning. Because most servers are designed for performance, so they don't necessarily optimize for energy. Laptops, on the other hand, because they're battery powered, it's the opposite. Okay, to increase battery life, they will aggressively spin down the disk. Okay. So assume the disk is spinning for now, it doesn't stop for any reason. We want to reduce the access time. Okay, remember, if the disk spins down, the access time goes up even more. In addition to the seek time and the rotational latency, there is going to be a spin up time, because it has to start up and start spinning at a steady rate before you can do anything. So that is going to further slow down performance. Okay, but assume it's spinning, you don't have to spin it up. What can you do to make it faster? You can make the disk smaller. So as I said, if you make this platter smaller and the recording more dense, then there is less seek. okay, because you are basically, there's less distance to traverse to get to the right track. Okay? You can make them spin faster. Okay, that means there's less rotational latency. If you double the speed, you will basically have the rotational latency. Okay, you can schedule disk operations to minimize disk head movement. That's the point that we are going to focus on today. You can lay out data on nearby tracks. Okay, we talked about that last time. You have a file that is for files that are accessed together, you can store them or cluster them closer to one another on disk. Okay, that's going to reduce the time to access all of that data. You won't actually move the disk and back and forth and incur lots of seeks. Okay? So you can place commonly stored files on either the outermost tracks or the innermost tracks, very clustered close to one another. Okay? You can also choose the sector size carefully. Okay, the sector size will actually dictate how quickly you can read a block of data. The smaller the sector, the faster you can read it. Okay? But if you make it smaller, then you are basically wasting a long seek and reading a very tiny chunk of data. Okay, so if you make it bigger, you can amortize the seek and rotational latency over a larger transfer, because the sector is the smallest granularity of data transfer. Okay? That's the minimum data you have to read, even if you requested only 1 byte. Okay? So these are all factors you want to optimize disk performance. As I will talk about at the end of this class, now that SSDs or solid state disks have started becoming common, many of these characteristics are no longer necessary necessary to optimize from an OS standpoint, because SSDs don't spin. They are solid state disks, they are no moving parts. You just access blocks and read them like you read address memory. Okay, so all of the discussion actually assumes traditional disks, okay, that spin, and then later on we'll talk about what to do if you don't have these kind of disks. Okay, so what we are going to do is only talk about this. So all of these other things are technology based. Okay, so you can only optimize this when you buy a new machine or buy a new disk and put it into a machine. Okay? Once you purchased a disk, you can't make it smaller, you can't make it spin faster, you can't lay out, you can do the layout, but you can't change the first 2 things. So those are hardware dependent. Okay? So the only thing that the OS can do is either schedule the disk operations or have the file system do some clever optimizations on where it stores data, so you incur fewer seeks. The file system optimizations we sort of talked about last time, so we are not going to come back to those again. We will only talk about this point, which is how do you schedule disk operations, how do you schedule disk operation to minimize disk head movement. So this is referred to as disk head scheduling. Okay, so what does that mean? So let's assume that the disk is spinning and the OS is sending requests to the disk, because there are lots of processes running in a system. You may be having page faults where you have to go and read a page. There may be other applications reading or writing files from disk. So typical disk will see multiple requests, multiple IO requests from different processes. Okay? They just arrive as a sequence of requests to the disk. So if the disk is concerned, you'll just receive requests like read a sector from track 10 and it's sector number 5, or read a sector, route 2 sectors from track 20 starting at sector 90. Okay, so you receive requests in this form. The disk doesn't care about which process or application made those requests. It's only concerned about reading or writing sectors. Okay. Now assume you receive a sequence of these, a steady sequence of these. The question is in what order to schedule them. And as we will see, the order matters. If you don't do something clever, you will actually incur more seek and rotational latency over it than you have. Okay. So we'll see how to optimize this retrieval of disk blocks from the disk, okay, and how do you reduce the seek time in the process. So we'll look at several techniques. First one is first compressor. We'll look at one called shortest seek time first. We'll look at one called scan or elevator scheduling, and we'll see several variants of scan. Okay, but just to give you a sense of why we need to do this, let's start with the simplest one, first come first serve. Yeah, so we'll assume, so this is basically a layout of a disk, although the disk is actually circular. The disk is circular, I'm just showing the tracks. Okay, so think of it as one slice of this disk. You're going from the innermost track 0, in this case to track 100. So you'll assume there are 100 tracks, and you're just going back and forth. Okay, so that's basically the layout here. Okay. So you are assuming, and right now we are going to ignore rotational latency. We are only going to look at requests in terms of which track they are currently on. Okay. If you add rotational latency, you have to do additional optimizations which we are ignoring for the moment. Okay. So we assume that you get these requests. The first request is go to track 65, read a sector. Then you get a request saying go to track 40, read a sector and 18 and 78. Okay. So if you simply did, and we'll assume that when the first request comes in, the disk head is here at track 30. Okay. So if you simply did first come first serve scheduling, you are actually going to cause the disk head to seek to precisely those tracks in that order. Okay, so you are going to go from track 30, you are going to actually go to track 65, and you are going to go outwards, that's your disk. And then you are going to go back to track 40, and then you are going to continue, go to track 18, then you are going to go along, make a long outward seek to track 78. Okay, so these are all circles. Okay, so you are just moving the disk head back and forth. Okay, is that clear? Okay. So then basically the question is, what is the overhead that you have incurred? Not in terms of times, but let's just count the overhead in terms of how many tracks do you actually have to traverse. This is a path that the disk head has taken. Move forward, back, and all the different. Okay, so if you go from 30 to 65, so initially at 30, the first seek takes you to track 65, you have traversed 35 tracks. Okay? Then you go from track 65 back to 40, which is this one. That requires you to traverse 25 tracks, and then you go from 40 to 18, it's 22 tracks, and then you go a long seek from 18 to 78, that's 60 tracks. Okay, so in scheduling these requests, you traverse a total of 142 tracks. That is the seek overhead in terms of tracks, not in terms of time. You can translate that to time, but we'll ignore that for now. Okay? So FCFS scheduling incurred 142 seeks to service those 4 requests. Okay? So we'll come back to this point about light loads and SSDs. Let's just see what we can do better. Okay? How do we do better? So rather than actually scheduling requests in the order in which they come in, what other things can you do? SSTF stands for shortest seek time first. Okay, so basically it's what's called a greedy algorithm. If you've taken 311, you probably know what greedy algorithms are. Okay? So what does it do? It says what are the outstanding requests that have arrived at the disk. Where is the current disk head at the moment? Okay, and then it will say which is the nearest request, and it will go service that. Is that clear what I just said? What shortest seek time first is where is the current disk head? In this case, you would say it's at location 30. Okay, what are the outstanding requests? Let's assume all 4 requests arrive at once in this order. Okay. So you look at this, saying what are the outstanding requests? There's a request at track 40, there's a request at track 18, 65 and 70. You say if I'm currently at track 30, what is the nearest block I can fetch from these 4? Okay, so the nearest one has to be this one. Of these 4, they're basically going to go to track 40. That is 10 tracks away. This request is 12 tracks away. That request is 35 tracks away. And that one is 48 tracks away. Okay, so you'll basically go service this one first. Okay, that's the one with the shortest seek. Okay, and then you repeat. Once you're done with that, you say now what are the requests? So in this case, no new requests have come. You still have the other 3 remaining. So what's the next one? Okay, so now if you are at track 40 and you have to service either this one, or this one, this is 22 tracks away and that's 25 tracks away from track 40. Okay, so you're going to go back here, service that. So that's why you got a 22 track. See? And then from here you're going to basically go back to 65 and then 70. That clear? So if you actually sum them, you'll see that your seek overhead has gone down to 92. In the FCFS, you had a seek cost of 142. Okay, that is reduced to 92. Same request, you just service them in a different order and you reduce the seek over. Yes.
Are all of these scheduling algorithms on disk or on the operating system?
That's a good question. The question is, who is doing this? Is it actually happening on the disk or in the operating system? The real answer is a bit of both. It depends on what the disk can do and cannot do. If you buy very cheap disks, the disk controller will not have this level of, may not, I shouldn't say will not. It may not have this level of sophistication. It may just have a very cheap controller that can only do FCFS scheduling. In this case, the disk driver can actually do this. You can have a queue of outstanding requests. Rather than issuing requests in FCFS order, you can reorder them and issue them, and you will get the same benefits. Okay? If you have a sophisticated disk controller where this kind of algorithm is implemented in hardware on the disk controller, then the disk driver can be dumb. It can just merely forward requests and say, you take care of it, you figure out what you want to do. Okay, so it will depend. It depends on if the disk is dumb, you can make the driver smart. If the disk is smart, you don't have to do much in the driver. Okay? But regardless, if you do this optimization, whether it's in software or hardware, you can actually get these benefits. Okay? But for the purposes of this class, we don't need to worry about is the OS driver doing this or the disk doing this. Let's just assume that there are requests coming in. Somebody is trying to figure out whether it's OS or the controller, what order to service them. And the goal is to reduce the seek overhead. Okay, so let's ask, so this seems to be doing better than FCFS. What are the problems with this approach? It's a greedy approach. Right? By greedy, we mean at any time you look for the closest request and go and just service that request.
Just because it's the closest request, like it can introduce more problems because if it's far away from the other two closest ones, then you kind of messed yourself up. Whereas if you started with like 18 instead of 14 or 40, you'd probably be better off.
Okay. Any other thoughts, comments, or problems or benefits of SSTF? So let's say that's the disk.
I don't know how much time it takes to do the math versus the actual seek and like
Math is not that bad. Compare. It was just mere comparison or some, in some sense. So let's assume that math is fast. Okay, mechanical movement, moving parts of the slow parts. Okay, let's assume that the disk head is here. Okay, and there's a bunch of requests coming. There's one here, one there, one there. Okay. So if you have SSTF, typically because it's doing busy scheduling, okay, it always goes and looks for the closest request. So as was pointed out, if your request on either the innermost track or the outermost track, those are typically going to be farther away than some requests that are in the middle tracks. Okay. So on an average, SSTF will favor nearby requests, and if you have a steady stream of requests that are coming in that are positioned on the middle, if you think of the disk as the inner third, the middle third, and the outer third, if you have a steady stream of requests that are coming to you that are sitting in the middle of the disk, and those requests will get favored over other requests that are on the innermost or the outermost tracks because they require a long seek. And as a result, you may actually get starvation. Okay? Very similar to shortest job first. This one is saying nearest job first, nearest block first. Okay, so if you do nearest block first, then blocks that are further away or tracks that are further away are going to basically get discriminated against and might even starve. Okay. So as is the case in any greedy algorithm, you probably will have problems if you don't get, if you're under heavy load and you get a steady sequence of requests that are close to wherever the disk head is currently positioned. Okay. And on an average, this will tend to favor blocks that are in the middle, but they will require shorter seeks from anywhere on this than tracks that are further away. Okay. So potential for starvation, obviously there. It will minimize seek time. Okay. as has been pointed out, it's a greedy algorithm, but it may not necessarily minimize overall cost. Okay? What does that mean? What is the overall cost?
So it will minimize the cost for the next seek, but it may not minimize the cost for all of the seeks it needs to do, because it can end up going back and forth more than it needs to. If it takes one to this side and then one to that side and then one to this side and then one to that side working out, it will end up zigzagging. Whereas if it had just started on one extreme end and worked out, the total amount of seeking would be less.
Okay, that's a more subtle point, and we'll address that point, which says you may actually have more seeks by just moving back and forth than if you had done a sweep. Just swept from the innermost disk to outermost disk. We'll talk about the sweep style algorithms in a moment. But the point here is saying you minimize seek but not overall cost, and you know,
That doesn't minimize rotational cost either? Is
Yep.
that what we're saying?
so overall cost, as I said, is seek time plus rotational latency plus transfer time. Right, so this is the I/O time. Right? Seek, rotational latency, transfer. Transfer time is the same. You're reading one sector. It doesn't matter what disk scheduling algorithm you use. You always read a sector at least. Okay. SSTF is only minimizing this. It's not actually looking at rotational delay at all. Okay. So you may actually get lower seek, but you may increase the rotational latency. Okay. There's a variant of SSTF which I have not put in the slide, but let me mention, which is called SAT, shortest access time first. Okay. Which basically says I'm going to look for the nearest block, but by near I mean the sum of the seek and the rotational latency. Okay, so from my current position, I say how much time, the seek time and rotational latency will it take me to go there or here or here or here. You compute that, and then you say I'm going to now find the nearest block, not just how much time it takes me to see. Clearly that's a more complicated technique because you have to take into account the disk is spinning. Okay, so when you arrive at a track, which sector am I going to be on, how much rotational latency is it going to take me, all of this has to be figured out. Okay? And once you figure that out, you can actually go and do the right. So it is more complicated. Most disks will not implement this in hardware. It's far too complicated to implement. Even implementing in software is non-trivial because this requires you to solve a problem called the traveling salesman problem. Not sure if you did that in 3 levels. The TSP is, you cannot have efficient implementations of TSP. Okay, you can only have heuristics to do TSP. Okay, so because it's NP. Yeah, so typically you will not actually implement these kinds of algorithms, but if you really wanted to optimize the disk, this is what you would have to do. Okay? And that you can show as optimal in some sense. Okay, okay, you had something?
Yeah, I was basically asking the same thing.
So SATF, this is just as a side note, if you actually wanted to implement overall cost, you would have to modify SSTF and not say which is the nearest block from just looking at seek, but you have to say which is the nearest block such that the total seek plus rotational latency is the shortest to that block. If you do that, then you get a variant which is going to be even more efficient than SSTF, but far more complex, because computing that is a non-trivial problem. Okay, so now we will come to a different algorithm which was alluded to earlier. This one we will call scan. Okay, these have different names in the literature. Okay, it is also called elevator scheduling. Okay, because this is the algorithm that elevators use. If you're an elevator, there are people that are hit some buttons, that's the algorithm that an elevator is going to use to service them. So think about what an elevator does. Okay, it always starts from the lowest floor. And if either somebody gets in the elevator or somebody pushes the button on any floor, it just starts moving up. Okay? And as it moves up, it will start servicing requests. Okay? It always keeps going up. Okay? And then once it's reached either the top floor or there are no more requests, it will change direction and start going down. Because it's just scanning floors up and it goes up and it keeps coming down. So it's just scanning for floors where it needs to service someone. Stops there, services them and moves on, and it will change directions. Same is true of scan. So what scan will do is you will always start on the innermost track. Okay? And you just start sweeping outward. You just start going out, and as you reach a track where there is an outstanding request, you stop. You service that request and you continue scan until you reach all the way to the end. Okay? Once you reach the end, you change direction and you start scanning backwards. Okay? So that's called elevator scanning. Okay, so you'll just scan from 0 to 100 in this case, and 100 to 0. And as you reach a track where there is an outstanding request, you stop, service, continue. Okay. Simple algorithm. In terms of implementing in hardware, there isn't much to do. Just have to keep track of what are the requests, keep them in sorted order, and you're done. Okay, so let's look at the same scenario. You are at track 30 and you have these outstanding requests. Okay, so which request would you service next?
Track
15.
You are on 30.
which direction?
First thing you should ask is which direction are you scanning? But the answer will depend if you are scanning outwards or inwards. Yes.
So you start at 0, right, and then you scan outward, so you could start at 18.
Yeah, so if you had started at 0, then it would be different, but we are basically continuing that same example. So we started for whatever reason at 30. So we have to assume that you are at 30, you're in the middle of a scan, and this is what is actually happened. So we are assuming that you're in the middle of a scan. In this case, you're assuming that you're scanning inwards to the innermost track. So this is what you have received. Because you have to do this algorithm no matter where you are. You can't say wait until I go to 0, then start. Okay. So you are at 30 and you're scanning inwards, so that means the next one is going to be 18. Okay, so you scan to 18. Okay. Yes.
So this depends on like which way it's initially going. Because if it's initially going inwards and then starts at 18 and then goes back towards the rest of them. But if you start going outwards first, if it was initially going outwards, then you do the 3 on the outside and then go all the way back to 18.
Yes.
Right?
So if you are actually here and you're scanning outwards, you would have done 40, 65, 78, switch direction, come all the way back to 80. Okay. Now I should mention that there are several variants of this algorithm. Okay. Here we basically said after 18, you can switch direction, okay? And that's a variant. The variant says if after 18 there are no more requests, should you go all the way to 0 and then switch directions, or can you switch directions at 18 and just go back? Okay. And depending on whether you do one or the other, you have a variant. There's something called look and which is something called scan. Okay. In one case, it doesn't matter even if there are no other requests, like an elevator. It always comes to the ground level before it actually goes back up, even if there's nobody there. Yeah, because it is designed to do that. Okay, that may, so in this, if you did that, then after 18 you would have to actually, you would have 36 additional tracks. So you'll go to 18 and come back, and then you will start servicing the rest. Okay. But an optimization of this algorithm is where you can switch directions if there are no more requests that require to go further out or further in. Okay, if you have that optimization, which is what is actually shown here, you would actually switch directions at 18 itself and start going to 40, which means there's only 22 seats. If you went all the way to 0, then you would have to add 36 more tracks there, yes.
Is there actually a momentum consideration when you're considering the movement of the head? So
Is there a
so you said we have to go back to 0 in some cases and then go all the way up. Is that because of just technology? People want to make sure that we weren't switching directions?
No, it has nothing to do with technology. Simple algorithmic consideration where, for fairness, do you always go all the way to the innermost track and then start? Okay, because it might so happen that you decided to actually switch direction and go, and then a request suddenly appeared here. And it would, because then you would have to wait all the way to go back and come back in. So it is really has to do with fairness in terms of, you just ignored some floors. Right, so then it's like you are on the 90th floor of a building, the elevator came all the way to 89, you just switch direction and then you hit the button, and you have to wait for it to go all the way down and come back up. Right, so if it had just gone up, maybe from a fairness perspective, it is actually giving each floor or each track a chance. If there are no requests, you just skip. So that's really what it is, and nothing to do with technology. Yes.
Seems like if you were using this scheduling algorithm, if you had a policy to write non-sequential blocks over, a range of tracks, that you could further optimize this, is that?
Come again, I didn't get
So
what's the
ba-
optimization you're proposing?
So if you had a writing policy of when you're writing blocks of data to disk, if
Yep.
they're non-sequential blocks, and you're assuming that you're going to be accessing them randomly,
Yep.
and if they were clustered over a small range of tracks, then you could further optimize this?
You can further, well, how would you want, this is already,
Because if you're sweeping and you're assuming you're going to be getting random requests, then you're sweeping over a smaller space.
yes, you will have to sweep over a smaller face, so that's indeed going to reduce that overhead. But so will SSTF, because by definition it has to do fewer seeks if they are clustered together.
So is this just a read operation at the moment?
It doesn't matter. We didn't say that these are reads or write. Reads or write take the same time. Once you are positioned on a sector, whether reading the bits or writing the bits, you have to read and write at the same rate.
I was wondering, like, actually, if we were deciding which blocks to write out, getting
Yes, so he is saying, how do you actually decide, how does the file system pick which blocks to allocate at all? That is done independent of the scheduling algorithm. Okay? And the idea there is the more you cluster, the better your performance will be, because by definition, if you're going to access them together, there will be fewer seeks and more chance to optimize performance. So all algorithms will do better if you cluster your data that you access together. Okay, so this is scan. There's yet another variant. So I talked about scan, I talked about optimization of scan. We said don't go all the way to the end, switch directions. If there are no more requests in the direction you're sweeping, you can switch and start sweeping the other way. That's one optimization. Here is another one, which is called C-scan. And then there is a version of this called C-loop. It does the same thing. What C-scan says is that you will only service, so you will actually scan in one direction and only service requests whether in one direction. In the other direction, you basically go all the way to the beginning and you don't service. Yeah. So think of this as an elevator algorithm where the elevator only stops on floors as it's moving up. When it's moving down, it basically ignores people even if they're waiting, and they have to wait until the elevator starts going up again. Is that clear? So in this case, you will assume that you can assume that you only start servicing requests when you go outwards. So you will start from 0, you will keep going outwards, and as there are requests, you stop, service them, continue moving, etc. You go all the way to the end. Okay, and then you switch direction and you just do a quick sweep back to the first track without stopping. You just return and then start servicing again. So you never service on the way back. You only service in one direction. Why is that even worth thinking about? Yes.
Well, it was the case where you said, it just passes your floor at, floor 1, and then you press the button. If it does the other way, you'd have to wait for it to go all the way up, service everything else coming down, and you wait for a long time. And I think this tries to address that. When you go to the top, it comes back to this, which has already been waiting a long time.
So the same thing is mentioned here. Basically, this is mostly a fairness optimization. If you only sweep in one direction, or not sweep, if you only service requests as you sweep in one direction, what that does is it gives you better fairness in terms of how long a request has to wait before it gets served. Because if the diskette just happens to pass you, you have to wait for it to go all the way to the end and continue servicing requests on the way back until it hits you. Right? So there are what would happen is a lot more requests would end up waiting at this end when the disk is at the other. On the other hand, if you just sweep one way, everybody has to wait. If you just pass by, you basically have to wait for one sweep time before your service next. So outer or inner tracks don't get favored. In a pure scan, if you're on the outer or innermost track, you may actually get favored, because if the diskette has just gone by, you'll go to the last track, switch and come back and service you. Okay, so the wait time is much lower than if you have to wait for a whole scan. So this is done for more of a fairness reasons than, so there are more uniform wait times in this case, okay, than scan. Okay, so now looking at the same example, we will now say how are you going to service requests. So here we are at 30, we are assuming this case, let's assume we are going outwards, and you only service on the way out. So what you would do is you would go service 40, 65, 78, then you do a big seek back, and you are going to actually service 80. And that is not. Okay. If this is an optimization where you actually don't have to go all the way to 0, you only go to the first request and then you switch direction. If you had to go all the way to 0, from 78 you would come back to 0 and then go start scanning again and go to 80. Okay. Same optimization that I talked about in this slide, where you don't go to the end, you can switch directions if you reach the first or the last request. So if you do that, this is what you're going to get. 108 is your seek over. Okay, so we looked at 3 different algorithms and several variants of the last one. Scan, C-scan, look and C-look are variants where either you actually go to the end or you switch directions if you reach the end. There's no need to go further because there's no work to do. Okay, so this is what was actually being asked here, which is what can you do from a layout perspective to actually optimize performance. Okay. Now it might seem that a contiguous allocation of blocks on sectors may be a good idea because there is no seek between successive sectors. The next sector starts or the previous sector left off. Okay. But what happens in practice is that's not as good a technique, simply because you either need the OS to be to react faster than the rate at which disk is spinning. Okay, let me explain what I mean by this. So let's assume the disk has that. Okay, this is sector I. This is sector I plus 1. So let's assume that you stored a file in these two contiguous sectors. Okay, well, this is a block of the file, this is the next block of the file. So if you are reading the entire file, you would actually send requests to read from these successive sectors. Now in theory this may sound, as I was saying, good because there's no seek from here to here. This block begins where this block left off, this sector begins. Okay. Now what happens in practice is the disk is actually figured out, it wants to access this, it's reading this. Once it's read this, it's going to go back and say what is the next request. Okay, what is the closest request or whatever. You will basically say that's I plus 1. Okay. But the disk hasn't stopped, it is continuously spinning. So if you don't do this, make this decision near instantaneously, the first bits of this sector would have already started spinning by. Okay, there's no gap between this bit and this bit. If you stopped at this bit, if you cannot instantaneously figure out I need to continue reading, this bit would have actually spun by. So then you have to wait for an entire rotation again before you can read the next sector. Okay. So what seemed like a good idea, which was let's store these sectors contiguously, can actually harm you in some ways if the disk electronics isn't fast enough to figure this out, and typically it is not. Okay, so would you go ahead? Yes.
So, I mean, it kind of seems like it's not that bad because the rotation of the disk is pretty fast, right?
Rotation of the disk is fast, but it takes till 4 milliseconds to spin, make one spin, right? So the optimization here is what that is actually used in practice, what is called interleave. We say don't store blocks contiguously, skip. Okay, so if this is I, then you can actually, if you have two-way interleaving I plus 1, you skip a sector. So in the time it takes you to actually make the next decision, you can actually skip a sector, and by the time this sector comes by, you are ready. Okay. So this is basically called interleave. So we say don't allocate contiguous block or sequential blocks contiguously. You can have one or two-way interleaving where you can skip one or two sectors at a time. So you are basically record on alternate sectors for a single file. Okay. This sector can be used to store some other data that is independent of this sector.
Couldn't we get around that by just always buffering how many bits it takes to make the decision?
Yes, so I'll talk about,
read over by 10 bits.
yes, so I think that's coming next. Okay, so this is, so if you did no other optimization, this is what you would have to do to actually optimize performance. You just skip a few sectors, so you give the disk or the device driver enough time to send the next request and for the disk to figure out what to do, etc., etc. Okay, now, that's one technique. The other technique that was being pointed out here is that if you're already here, and if you have a large enough buffer cache on the disk, and I said we have 4 to 8 megabytes of cache, why bother? Okay, just read that entire track. You already spent enough seek time to get to this. Even if you're not requested it, just read the whole thing and store it in your cache. Okay. And then if you say what's the next request, and you say it's the next sector is already sitting in the cache. You don't have to wait for it to spin. Okay. This is referred to as read ahead. Read ahead is essentially what's called prefetching. Okay. You're prefetching data under the assumption that it is likely to get access. If your optimizations like contiguous allocation or whatever, it is likely that if you access sector I, some nearby sectors might also be requested at the same time. So if you already spent 4 milliseconds or 8 milliseconds seeking to that track, then read that whole track, cache it in memory. You have enough cache sitting there for you to temporarily store it. And if no request has come, you can discard it. You don't have to keep it there. You can just discard it later on. Okay. So prefetching of sectors is, or what is called read ahead, is an optimization that the disk often performs. This is why there is that, if you look at that chart I showed you, this is why you have these buffers of 4 and 8 megabytes. This allows you to prefetch data and store them there. The 8 megabytes typically means you can store several tracks in there. So then if there are any subsequent requests, you can service them immediately. Okay. If you add prefetching or read ahead, you don't need interleaving. So by definition, you're going to just read more data than was requested under the assumption that that's not a whole lot more work, so let's just do it and see if the OS is going to request that data somehow. Okay. So this is hardware level or disk level read ahead. This is somewhat different from what the file system can also do something called read ahead. Okay, what happens in a file system is if the file system actually sees that your process is reading this file sequentially, okay, it will try to prefetch data for you ahead of time. It will start sending requests for the next few blocks of the file, even though you have not, you meaning the process has not actually requested. Okay. It is also trying to do similar optimization. The idea being, if I can predict what your next request is going to be, let me issue it for you so that the data is already in memory even before you requested it. And this will improve your performance. Okay. This can only be done for sequential access. If you're doing random access, you're out of luck. It's hard to guess what your next random request is going to be. Okay. But for sequential accesses, you can basically do this at the hardware level, read the entire track. You can do that at the file system level where you issue requests on behalf of the process even before the process has requested it. Because it's a good bet that you are going to request it and the OS already has your data for you in track. Okay, so these are some optimizations you would do. The reason you have to do all of these optimizations really is disks are slow devices. Okay, and they have idiosyncrasies like disk is spinning. If you don't make decisions in time, the data you're trying to read is already spun by. You have to wait again for it to spin by. So because of all of these characteristics, you have to go through great lengths to optimize your I/O performance. Okay? The file system will also try to cluster your data close to one another on track so you get good performance. So a whole lot of optimizations going on just to improve this slow disk reads and writes. Okay. So now we are going to switch gears and have one slide of discussion on solid state disk. So most of what I said so far is pretty much useless for SSDs or solid state disks, okay, because they use a completely different technology. Yeah. SSDs are like these SD cards or micro SD cards that you put in your phone or camera. Okay. They are basically a chip that has recording capabilities. Okay. No moving parts. Basically all you send a request is give me block I, it will basically go read the data for block I from that right location. Think of it as a persistent memory. It's like RAM, you can address, just as you can address RAM and there's nothing moving as far as RAM is concerned. Same kind of stuff, SSD is not volatile. Data doesn't go away if you power something down. Now not most, but lots of devices have started using solid state disks. And there are most phones and tablets use SSDs. If you have iPods and things, devices like that, they also use SSDs. Laptops have started using SSDs. This machine doesn't have a moving regular disk, it has an SSD. Okay. And there are good reasons for using SSDs because there are no moving parts. So all of the things I was talking about, if you drop it, then it may damage the disk. Those things don't actually occur when you may damage the machine in different ways, but you're not going to have the disk head pierce the platter or some such thing. Okay. So now the main advantage of SSDs are they're much faster. You don't have to pay for this slow seek. Okay, you just say read block I and you just go and read the bit stored at that location. Okay, this is effectively random access. Right? Quick random access. There's no seek to optimize, no rotational latency. So reads are extremely fast. Okay, so if you have an SSD and you actually compare the performance of an SSD and traditional disk, you'll see that reads are very, very fast. Random reads are even faster because there is no difference between random reads and sequential reads because there's nothing to move. Right? In a random read, your disk head is moving back and forth. Okay, here you just say, give me block I, there's no overhead. Okay, I'm saying the block I is close to where you read the current block or not. It's the same thing. Now, SSDs and flash, which is a technology that they use for storage, do have one idiosyncrasy, which is writes are very slow. And the reason for this is the technology requires that before you overwrite any data you have already written to, you have to subject it to what is called an erase cycle. Erase essentially says go scrub that region. Okay, it's going to actually use some electronics and start zeroing things out and basically cleaning it up, and then you can overwrite. Okay? This is not required in magnetic disk. You can simply go and write whatever bits you want on a sector. Okay? And it will just overwrite whatever was written there. You don't have to go and erase that sector before you overwrite it. You just say write these bits, you will just go write those 5 bits at that sector. Okay? So erase cycles are very slow. Okay? Orders of magnitude slower than reads and writes. Yes?
So why does it need the erase cycle?
I'm sorry?
Why does it need the erase cycle?
Why does it need the erase cycle? That is a technology limitation. The technology says that once you have written some values to this location, you have to reset that so it becomes ready to write again. You can't just write. Hard to explain in an intuitive way. That is the way the technology works, which is before I write there, I need to scrub it so that it becomes ready to receive new bits. That's the crudest way of putting it. Okay? So that's one limitation. Second limitation is most of these compact flash disks have a maximum limit on the number of times you can write to a sector. So once you exceed that limit, then the sector basically becomes useless. You can't write to it again. It's basically used up its number of cycles. This is similar to batteries on laptops which can support, let's say, 3000 charge cycles. After that, the battery capacity is dead. More or less, you have to replace the battery. Same kind of stuff here. And typical write cycles are like 100,000. So you can write to a block 100,000 times. After that, the block is locked. You can't write to it again. So you have to, you don't have to worry about disk head scheduling in the case of SSDs, but you do need to worry about these two technological artifacts, okay, which is, first of all, overwriting to a block is almost a no. You don't do it. Okay? And second of all, you don't want to keep writing to the same block over and over again. If you write to a block too frequently, the lifetime of a block is limited. Okay, so you want to basically optimize for these two things. Okay, so let's ask, what can you actually do to mitigate these two effects? Okay, if writes are slow, not writes, since the writes are slow, the rewrites are slow. Now, writing to a blank sector is very fast. That's not a problem. Okay, once you are written to a block, if you go change that data, let's say you go change something in your source file and write it back, you go and try to overwrite that block, that is going to be very slow. It requires an erase. Yes.
So just write it to another sector and mark that old one as unnecessary.
So basically what happens in SSDs, as is being pointed out, is if you want to overwrite some part of a file, okay, you don't go back and rewrite that sector that you had written to. You simply move that data somewhere, you write to a new empty sector. Okay? And then you will simply mark that old sector as deleted somewhere. Okay? And later on, you are going to basically have a process in the background which does garbage collection. It goes to all these deleted sectors and slowly runs an erase cycle and cleans them up for subsequent writes. Okay? So in this case, what happens is as you keep changing, modifying a file, you are not going to go and write the new data to the same location. You are going to just find a new empty sector and write it there. Just mark the old data as gone. Okay? And some other process is going to run a garbage collector for you. So it said do not overwrite, write to a new location, garbage collect later. The reason you do garbage collect later is erase cycles are slow. So whenever the disk is not seeing any request, you can run the garbage collector on the disk. Okay, it's going to go and start erasing some blocks and freeing them up for subsequent use. Okay? That's the first optimization. That will address this problem. What do you do to address this problem? Yes.
You choose which disks you want to write the data to based on how many times it's already been written to. So we want to do leveling. We want to write to the disks that have been written to the least number, the sectors that have been written to the least number of times.
Okay.
So that we wear the disk down evenly instead of ending up with always writing to some specific block, and then having that one wear out completely while the rest of the disk is still okay.
Okay.
I was just gonna say, you could like have policies where you try to do more stuff in memory where you can, rather than using the disk as a cache, or using
Okay.
the memory as a
You
cache.
can do more stuff in memory and write less frequently or something else.
If you, that's where the random write comes from. It's like that's if you, like just like don't constantly write on the same spot, but like just write on different space, then you will eventually expand the lifetime of the document.
Okay. Alright, so basically these suggestions are indeed what is actually done in the hardware. So most flash devices, whether this is a flash chip that you put in your camera or this SSD thing, disk on your machine, will have sophisticated algorithm to extend the overall lifetime of the disk. Okay? So basically you want to write evenly or age all the sectors in the disk evenly. By age, basically you mean how many times has it been written to. You don't want some sectors to have a much higher age and other sectors to have a lower age. So if you have a file that is constantly being modified, okay, the blocks of the file you want to scatter randomly across this. Okay. This is what is called wear leveling or load leveling. You spread the load, the write load across all sectors, so all of them age more or less at the same rate. Okay. And by doing this, you are going to increase the lifetime. Otherwise, what will happen is if you try to erase or some sectors more frequently than others, their age will increase more rapidly than others. And once they hit the maximum lifetime, that block will be dead. You can't use it again. So you don't want problems like that. So most of these SSDs, they will have controllers. The file system typically doesn't have to do this. This is all done in hardware. Okay, the hardware will implement some load leveling techniques for you. Yes.
What's sector size? Is about the size of the block, roughly?
The sector size, again, you can pick based on the technology. 512 bytes is what SSDs use because file systems and OSs are used to that. So, and you can pick it differently for other electronics, for instance. Okay. So whole new set of optimizations have to be performed here. So you have to do load leveling to ease the number of writes to a block. You don't want to overwrite because that's very slow. It's going to dramatically reduce your performance. You would rather write to a different location and go back and clean up the mess later by garbage collection. Okay. SSDs are typically used in applications that require very high I/O throughput. Okay. They are much more expensive than traditional disks. They're still factor of 5 to factor of 10 more expensive. They cost 5 to 5 times more for the same capacity, but they also give you much higher I/O throughput. Okay, so they are actually used in very high-end server applications. Okay. They're also used in battery-powered devices. The reason they're used in battery-powered devices is they're a lot more energy efficient. There's nothing to spin. There's no motor spinning and consuming your battery. Right? So it's more efficient. So they're used for two different reasons in two different class of devices. In server-end devices, you don't care as much about energy, but you do care about performance. And these do give you better performance. In low-end, not low-end, but in smaller battery-powered devices, they are more energy efficient. So even though they are more expensive, they can dramatically increase your battery life. Okay, so you put them in these devices for that reason. So those are the two main use cases for SSD. They're slowly sort of encroaching on SSDs, both at the very high end and the sort of the energy efficient end of the spectrum. Okay, so in 5 to 10 years, you probably won't see a whole lot of these traditional disks. What that means is the OS also has to evolve. A lot of the file system code that's been built on let's cluster the data together because it will actually improve I/O performance doesn't matter at all from an SSD. You can store data wherever you want, it costs the same. Okay. So a lot of that code is going to get defunct. Instead, you have to build file systems to deal with these other artifacts, which is slow writes and things like that. So that's SSDs. I'll quickly talk about tertiary storage and then maybe the RAID discussion can come later. Okay. Now, so disks are the most common storage devices, but there are many others. And they are often referred to as tertiary devices. The most common one is actually tape. Okay, tape disks or tape drives, which are used mostly for archival or backup purpose. You don't usually use tape drives to store live data. You just use it to store your backups and so on. Okay, so there's a price performance trade-off here. Tapes are used to be significantly cheaper than disks, okay, but also significantly slower than disks. Okay, think of a tape as like if you've seen a VCR tape. Basically, you have a recording medium, and then you have to scan all the way from the front to the back. Random access is very slow on a tape disk because you have to actually spin the tape to go to the right location to read it, just as you fast forward data. So it's the same difference between watching a DVD and watching a movie on a VCR. Same kind of considerations happening. In a DVD, you can random seek to any scene almost instantaneously. On a VCR, you have to fast forward and wait for 3 minutes before you get to the right location. Okay? But one is much cheaper than the other, or used to be. Okay? The price of disks have fallen so quickly that actually cost of disk and tape is now more or less the same, which is why you don't even see tapes anymore. People actually construct backup devices using cheap disks. Okay? They don't use high-end disks, they just say disks are cheap, so let's just use an array of disks and put all the backup data on it. But there are still applications where tape drives are used, optical disks and so on. Okay, so these are slower devices. There are different ways to schedule them. Okay, so if you actually have very large backup system, you have this thing called robotic tape drive. This is like a jukebox that you see where you can say play this song and it goes picks the right CD and then starts. It is effectively a linear access medium. It's not designed for random access, which means that the way you are going to read and write will require you to read or write sequentially. If you do random access, is very slow. For backup, that's okay because you're just sending a stream of files and you're just writing that sequentially onto a tape disk. And if for some reason your machine dies, you go and retrieve most of it again. Okay, so for these scenarios, it's okay. Okay, otherwise, the performance of random access is very bad for tape drives. Okay. So those are some other storage devices. As I said, they are mostly called tertiary storage because they store archival data. Okay, they are data that's backed up that you only get to once in a while. Okay, so I have 2 minutes, so I can do quickly RAID storage. Okay. Now, as I said, so higher end servers basically have two kinds of I/O needs. Either they need high performance or they need high capacity. Okay. If you need high performance, SSDs have actually been the way to go, although they don't offer as much capacity. But if you need higher capacity, the only way to actually achieve that is to use collections of disks rather than individual disks. Okay. So let's take typical disk. The biggest ones you can buy is 1 to 2 terabytes. Okay, so 2 terabyte disk is probably the best you can do today. Okay. What if you had a database that was 4 terabytes in size? No single disk can actually store that data. How would you store it?
Two disks.
Sorry?
Get two hard drives.
You basically have to split that data across multiple disks. Okay? And so now you could do that manually and say this part of the database is on this disk and this part of the database on this disk. But that makes applications and application design very painful. What you would rather do is just take a collection of disks, whether it's 2 or 5, and tell the OS saying go construct a bigger logical disk that just looks like a collection of these disks. Okay. So what the OS will do is it will create what is called a disk array. Okay. So from a OS standpoint, or the file system standpoint, this collection of disks appears as a single large logical disk. Okay. So basically you have the smaller disks. You constructed what is called a volume that will basically span this multiple disks, but the applications don't have to worry about where the data is stored. Okay, you basically just access this entire disk as if you access a single disk. You can just go address any block from 0 to n without worrying about which physical disk it's stored on. There's something called a hardware disk array controller, which is going to figure out saying block 0 is here and block 1 is here and block 2 is here. It's going to figure out which device it's stored on and it's going to retrieve that. So this is the reason you need additional hardware to construct what are called disk arrays. Okay. So disk arrays give you two benefits. They give you higher capacities than what a single disk can possibly give you. Okay. But they also, the other advantage, which is somewhat subtle, is they give you better performance than what a single disk can give you as well. Okay. Because these can operate in parallel. Okay. You can retrieve 4 blocks of a file from 4 different disks in parallel and get 4 times the throughput of a single disk. Okay, just as multiprocessor or multiple core machine, you can put all the cores to use. Here you can use your multiple disks. So they are going to give you better performance than a single disk. They're also going to give you higher capacity than a single disk. And you're going to get all of this without having to do anything from a file system standpoint, because there are hardware controllers that will actually do all of this for you. Okay? So this is basically going to bring us to this topic of disk arrays, and there's a lot more thing to say here, which we will keep that for next time. So I'll finish this discussion in the next class. Okay, so let's stop here.